Welcome to the course Molecular Communications. In the first class, we will review some basic concepts of communication systems. As I mentioned in the course introduction session, that communication is nothing but a process to send some information from one end to another end. And so transmit message bits containing the information need to reach the receiver end. And the environment in between can change or distort the signal. This environment is known as channel or communication channel. So we have some message bits we want to send, and I mentioned earlier the message bits can be a sampled version of some audio or a picture or any encoded message. So it goes to transmitter generates signal xt, and at the receiver you receive a changed or distorted version of this signal yt, and then receiver does some processing to generate the received information. And our goal is that the received information is same as the message bits. Then we say the communication is success. So the environment in between changes xt to a distorted version, which is yt. So we can represent this by another block, and we represent this as a channel. Let us look at the transmitter. Suppose you have a picture to transmit, and if the receiving end is at a far distance, you cannot send the picture directly. You have to convert that picture to a physical signal first. So what happens is that the transmitter tries to create a disturbance around itself in the environment. The disturbance then propagates to the receiver. Receiver receives that or senses that disturbance and try to decode what was sent. Again, the disturbance generated by the transmitter need to be correlated, or it should be dependent on the actual information you want to send. Now, what kind of disturbance you can create to the environment, that depends on the media and the process, and that is how we have different type of communication systems. So the process of converting the message bits to a physical signal is known as the modulation, and that signal is then transmitted via different mechanism using the actual transmitter. Similarly, when this signal, which is the distorted disturbance, reaches the receiver, it is first received, can be converted to some electrical signal so that the transmitter can process it. Then it tries to compute the actual message. So it's try to demodulate the signal, it try to extract the information from the disturbance, and that signal is whatever you received is then decoded to receive the actual information. So we will take an example of an RF communication system. So most of the modern communication system which you see around us, like Wi-Fi or your mobile, they all work on electromagnetic communication. This means the disturbance we are going to talk about is a disturbance in the electrical magnetic field around the transmitter. So once transmitter does that, a wave is propagated, a wave is generated which propagates to the receiver, which is then received by the receiver and decoded. So you can generate this disturbance from a physical signal using antennas, and same way you can receive signal. So whatever bits you have, it is first converted to electromagnetic signal, right? And then it is it is transmitted using some kind of transmit antennas. It propagates because of different various environment factor. The EM wave may distort, and when the receiver also receives electromagnetic waves using a receive antenna, which converts the signal to electrical signal, which is then demodulated. So let us look at the modulation more carefully. The modulator masses bits to physical signal, and it's a way to encode information into physical signals. So when we talked about the image, that's, as I said, any information can be represented in terms of bits. So what you have is just a bunch of bits, which is not a physical signal. Physical signal actually means a electromagnetic wave or a pressure wave, a sound wave, anything which is generated via, which can be sensed in the physical environment. So what we do is, we first identify a set of different physical signals which can be distinguished as the receiver. Remember, the goal is the receiver should be able to understand what was sent. If you send the same signal for different type of information, the receiver will not be able to guess that. So suppose we have a bit which can only be 0 or 1. What we do is, we need two different types of signals. We will send one signal corresponding to 0 and one signal corresponding whenever we want to send 1, and the receiver, it should be able to distinguish whether it has received the first signal or the second signal, and that is, it's know whether 0 or 1 is transmitted. You can think of it as a simple exercise where a city has been invaded. It wants to tell his friend city that it has been invaded. So whenever it's invaded, that is 1, and when it's not invaded, it's 0. So what city does is, it has two types of signal. It has a beacon on the top of the palace, a lamp. When lamp is lit, that is one signal, and when lamp is not lit, that is another signal. And what it says that 0 means when the city is not invaded, the lamp will not lit. So I want to send a signal where lamp is not lit. So there is no light which is transmitted from the lamp. But when the city is invaded, we want to send a signal, a light signal from the lamp, so we lit it. So we have two signals, x1t and s2t. These are distinguishable at the receiver, and we say that we map 1 to s1t and 0 to s2t, which means whenever we want to send 0, we will send s2, and whenever we want to send s1, we will send s1. Right, and this S1 and S2 are some time limited signal. So we would send this signal for some time. And so what modulation actually does, it converts your message bits, especially a particular bit 0 1, to a symbol. Here S1 and S2 are two symbols, and then this symbol is actually using some antennas or whatever your transmitter is, it is actually converted to physical signal which is being sent. Right. So this means we transmit S1t, if the transmit bit is 1, S2t is 0. Let us look at two examples. We have one pulse S1t equal to cos omega t and S2t is sin omega t. We transmit the cos omega t when we want to send 1 and sin omega t when we want to 0. So the receiver should be able to distinguish whether the cos omega t was sent or the sin omega t was sent, and based on it will guess whether 0 or 1 was sent. Similarly, another can be unit and no pulse. So you send a pulse when you want to send 1 and you send no pulse when you want to send 0. And if the receiver receives any pulse, it means that the 1 was sent. So this was for 1 bit. Suppose we want to transmit a sequence of n bits. So what we do is we create n time slots, one slot for each bit, and then corresponding to that bit and that particular slot, we will send S1 or S2. So what you get is a sequence of S1 and S2 signals in time. Each time slot is of the same duration as the signal, and receiver also do a slotted receiving. It divides its time into different slots. For each slot, it tries to guess whether S1 was sent or S2 was sent, and it decodes the bit. So eventually you will also get a sequence of bits at the receiver. Now if you have more signals, we can map these signals to bit patterns also. Suppose we have 4 signals, cos omega t, sin omega t, minus cos omega t, minus sin omega t. So here I can map 4 different states of transmit message to these signals. But we have only 2 bits. So what we do is we club 2 bits together. So suppose we have n bits. What we do is we create n by 2 pairs. Each pair has 2 bits, and that bit can be 00, 01, 10 or 11. And then we map, suppose 00 to S1, 01 to S2, 10 to S3, and 11 to S4. This means that whenever we want to send 00, we send S1. Whenever we want to send 01, we send S2, and so on. So in this case, you will require n by 2 slime slots to send this information. And again, receiver should be able to distinguish between all these 4 signals. Otherwise, the communication will not be successful. And here each slot, each is a symbol, and we send one of these 4 symbols in each slot. So we also call the slot as a symbol duration. So if we have n possible states of the transmit signal ST, this means that we have n different types of signals we can send as the transmit signal. Then this means that you can send log 2n bits in each symbol duration or each slot. So for example, if we have 2 types of states, we can send 1 bit 0 to 1. If we have 4 types of states, we should be able to send 4 different states of the transmit signal, which means we can send 2 bits, because 2 bits will make 4 different types of states. Similarly, if you need to transmit k bits, you basically would need 2 to power k different waveforms in each slot. Or of course you can send them one by one, then you only need 2 waveforms, but it will take longer time. Again, the receiver should be able to distinguish between these different waveforms for a successful communication. If receiver cannot distinguish them, then it will treat both signals as one. It's not able to find whether it was 0 or 1. And again, it may happen that even if you have chosen the distinguishable waveform, because of the channel in between the signal which is received is ambiguous, which means you are not able to distinguish between the 2 waveforms. We will talk about this in the later slides. Now, how do we select these different types of waveforms? That will define what kind of modulation we are using. If the waveforms differ in terms of phase, for example, one is cos omega t, another is minus cos omega t, then we call it a PSK modulation, which is phase shift keying, because we are shifting the phase for different types of waveform. So one example is which we call binary phase shift keying, BPSK, where you use 2 types of PSK. One is phase 0 or another is phase 180. You can also have cos omega t and sin omega t as 2 different phases. If the waveforms differs in the amplitude, it's known as ASK modulation, which is amplitude shift keying. Here, suppose S2 is cos omega, S1 is cos omega t and S2 is 2 cos omega t. If we're sending the same phase but we are using different amplitudes, then it's called a ASK modulation. The other one is on-off keying, where or called OOK. Here we on the system, which means we send pulse for one state and we send no pulse for the other state. So system either remains on or off. That's why it's called on-off keying. Now let us talk about communication channel. We said that a communication channel has an input xt, which is a transmitted signal, and then it has a received signal yt. And because of different environmental factors, yt is a distorted version of xt. If the channel is noiseless or perfect, then yt can be equal to xt. So yt does depends on xt. If yt does not depend on xt, then basically channel is not carrying any information. You receive signals totally independent of transmit signal, which means you are not able to send any information. So hopefully yt depends on xt, but is not exactly equal to xt. Due to different various environment factors, there may be some distortion, but it does depend on xt. So how does that it depends on xt? How does yt depends on xt? That relationship is exactly known as a channel, right? A relationship or a block or a model which can tell you what is yt given xt, which is known as the communication channel, and should be able to tell us the distribution of yt given xt. So suppose at any t, the received signal at that time is only dependent on the transmit signal at that time. We call such signals memoryless, which means that the output does not depend on any previous input, previous transmit signal. It only depends on the current signal. For example, yt equal to 2xt. So in that case, no matter what was sent a second ago, the received signal only depends on the current transmit signal. So for such signal, if you know the joint distribution or the conditional distribution of yt is equal to y, given that xt is equal to x, right, for every pair of x and y, then you basically know the complete channel. Another example can be, suppose the channel is such that it adds a white Gaussian noise. So white means it is not correlated, which means each sample of the noise is independent. And if you look at the correlation with the previous time instant, even if it's very close, there is no correlation. And Gaussian noise means each sample is Gaussian distributed. So suppose the noise is NT, right, which means for each t, NT is an independent Gaussian random variable. In that case, the received signal is equal to the transmit signal plus noise. So we call it additive white Gaussian noise channel or AWGN channel, and it is one of the simplistic yet very popular channel model which people have used to analyze various transmission methods and receiving schemes. Now let us look at the detection at the receiver. Suppose the transmitter is choosing two signals, cos omega t and minus cos omega t. So you can see that S1 and S2 are both cos pulses, but their phase is different. So at the receiver, we do not receive this signal, but we receive, suppose, a noisy version of that. So from the received signal, we try to estimate the phase so that we can guess what was being sent. So this is the received signal which you have got, and corresponding to S1, this is what you get, corresponding to S2, what you get. The receiver does not know whether S1 and S2 was sent. It just receives one signal, one of these two. And from these two, it tried to guess the phase. So there are multiple ways you can do that. I'm just going to talk about a very simple one, but there can be better methods also. So what we do is we just look at particular time t, okay, and then we see that what should be the value of the signal if S1 was sent and S2 was sent, and then we compare at the received signal the value and see whether the received signal is close to the value corresponding to S1 and S2. Right? And whatever it is close to, we call that S1 or S2 was sent, and that's how we decode the bit. So if we found that the received signal at that time is close to S1, we say bit 1 or the bit 2. Now I say close. What does this close means? I am going to talk about a little bit later, but it just means what received signal, what signal it corresponds to. Right? For example, uh, so if I take time at t dash, what I get received signal is yt dash. The transmitted signal at that time was xt dash, and the noise was nt dash. This is for the AWG channel. If I call yt dash y, xt dash x, and nt dash as n, this is what we get, y equal to x plus n. Received sample is equal to transmit sample plus noise. And suppose I choose t dash equal to 2 pi by w, which is like the end of first wavelength or first time period. So at that time, if you look at that, this is exactly how I marked it here. At the end of the first time period, if S1 was sent, you should get a signal close to 1, and if S2 was sent, you should get a signal close to -1. So this means that basically x is equal to 1 or -1. So we can say x is equal to 2b minus 1, and in absence of noise, y would also be equal to x. So y would be 1 if you have a bit corresponding to if you have bit 1, and -1 if you have bit 0. So we decide that again, this is an arbitrary decoding method. You can choose different ways also, but this is one of the way you can do, which looks intuitive, that if y is more than 0, you say bit 1. See, ideally you should get 1 and -1. If you get 1, the bit was 1. If you get -1, bit was 0. But because of the noise, you will get some distortion. 1 can become 0.8, right? -1 can become -0.8 or -1.2. Noise can be so much that sometimes 1 can also become -1. Right? But that is of course less chance. We assume that noise is generally 0 mean, here AWGN, so noise is 0 mean, and the probability that it's high is very small. So in those cases, there is a higher chance that the noise is smaller and 1 is generally distorted to around a value around it. So if you get a signal which is less than 0, there is a higher chance that the transmit bit was corresponding to -1 or bit was 0. So this is the intuition of the decoding here. We choose if the received sample is more than 0, we say bit 1 was transmitted, and if it is less than 0, we said the bit 0 was transmitted. So this is the rule. If I say x hat, which is the decoded bit, which is actually estimation of actual x, because we do not know x, so receiver makes a guess or estimate of x. We say that if x plus n is greater than 0, we say 1 or 0. So this is an indicator function, which means if the condition is true, it is 1, otherwise it is 0. So if x plus 1 or y is more than 0, we say it's 1. So x is nothing but 2b minus 1 plus n. So this means b plus n by 2. If it's more than half, the decoded bit is 1, otherwise 0. So if bit is 0, b is 0, this means that b hat would be, so the actual bit was b, and suppose the decoded bit is b hat, right? So you can say x and x hat, or b and b hat, both are same things. So if the you can talk in both terms, either x hat or b hat, both actually kind of same things. If you know that if x hat is 1, which means your estimate for b hat is 1. If x hat is minus 1, the estimate of b hat is 0. So this is what I am going to. So if b hat is equal to 0, so if b plus n by 2, if b is 0, it means n by 2 is greater than half, or n is greater than 1, then the decoded bit is 1. Or if n is less than 1, then the decoded bit is 0. Similarly, if b is 1, you have a different condition, because then you have to put 1. In that case, n should be greater than minus 1 for it to be decoded to 1, which means that if you transmit 1 and the noise is so much that the noise is less than minus 1, it can make this bit flip from 1 to 0. So if the noise is less than minus 1, right? I mean, and you add that, so it's a negative number which is in a magnitude is high, so it makes the signal from 1 to goes to below 0, so you will decode the signal as 0. So this means the bit can flip, which will result in communication error. And what is the probability of that? So suppose the probability that the noise is more than 1 is equal to P0, and probability that the noise is less than minus 1 is P1. So in that case, the receiver will make an error with probability P0 when bit 0 is transmitted. Why? Because when 0 is transmitted, there will be error when n is more than 1. So, and the probability of that is P0. Similarly, when bit 1 is transmitted, the error would be when n is less than minus 1, and the probability of that is P1. And if you have a symmetric noise, this P0 and P1 kind of same. So if you have a Gaussian noise with mean 0, you would expect the noise, these two probability to be same. So let us talk about this example where S1 and S2 are cos omega t minus cos omega t. So you have masses bits. When you modulate it, you get a symbol which is either cos omega t or minus cos omega t. Then use an antenna to actually transmit this signal. It's an EM wave. And then there is a AWGN channel which adds some noise at the reception. The antenna receives this signal and it has an electrical signal which is either a noisy version of cos omega t or minus cos omega t. At a demodulator, you sample the signals and look at its value at the end of first time period. And then if it is 1 close to 1 or minus 1, depending on that, you make a decoding and you estimate the value of bits p. So this is the communication channel, but we can also abstract this whole thing as the communication channel. See, this is the masses bit and this is what you received bit is, decoded bit is. So this is the receive and this is the transmitted. So you can treat the whole thing as also a modulator, transmission and decoder also a part of the channel. So it's a relation between B and B hat. So in that case, the channel will be represented by relation between B and B hat, which is the following. Given 0, the probability of bit receiving bit 0 or given b equal to 0, b hat is 0 with probability 1 minus p0, and bit is 1 with probability p0. Similarly, given the transmitted bit is 1, the received bit is 0 1 with probability p1 and 1 minus p1. So we can decode the symbol x also, which is the same as decoding the bit, right? Here there is a one-to-one correspondence between symbol and bits. So instead of talking about decoding the bits, we can also talk about decoding the symbol, and it has the same meaning. Just like our convention may little bit change. So here our transmitted symbol would be x and the received is y, and then in that case I will keep the modulation and the decoder outside the channel, and I will treat this whole thing as the channel. So it's a relation between the transmitted symbol and the received symbol, which is y. So again, what do you consider as a channel? That depends sometime on your conventions also, but it should be consistent, and basically it just means that some relation between your transmitted and the received signal. So here in particular, if x is minus 1, y can be minus 1 if noise is less than 1, and 1 if noise is more than 1. Right, again this is this is y hat, not this is again y hat equal to minus 1 1 if n is less than minus 1 or n is more than minus 1. So let us talk about this particular case where we treat receive symbol and the transmitted symbol. And here our goal is that given the value of y, we want to estimate the we want to decode x, estimate x, and call it x hat. So we saw that in the previous example we sample it. We compare output with 0. If it is more than 0, x is 1. If it's less than 0, x is minus 1. Right, and we have talked about it why this looks intuitive, because this is the this is closest to what you would expect, right? For example, if there are two values of y which are possible, 1 and minus 1 in terms of when there is no noise, and if there is some noise, 1 can change little bit and similarly minus 1 can change. But we hope that the noise is small. So it is more likely that the noise will be small and less likely that the noise will be more high. So if I receive a signal y equal to 0.2, right, and then when we look at the error, so if 1 was transmitted, we don't know what was transmitted, but we are just calculating. If 1 was transmitted, then this means there is an error of 0.8, right, minus 0.8 in particular. And if minus 1 was transmitted, there is a then the error is 1.2, and we say there is a high probability that the noise is small. So which is more likely, a noise of 0.8 or noise of 1.2? So that's why we said noise of 0.8 is more likely. That's why we expect that the transmit symbol was 1. Right, and similarly if the receiver minus 0.2, then the thing is reversed, and then you expect the receiver signal to be minus 1. So exactly at the boundary 0, right, if y is 0, it is at the same distance from both x, right, and if it is moves little bit up and down, it comes closer to one of the symbols, and when we try to decode that way. So this is just based on intuition, but there are lots of decoding method which is proved to perform up to some certain guarantees. So we'll look at some of them. So suppose we are assuming here that we know py given x, right? We know the channel, which means we know given any x what is the distribution of y. Right. So again, we do not know what is y. We just know what values y can take and with what probabilities. So given that information, now if I know y, how do I estimate x? We can choose a x which maximizes py given x. See, py given x is the likelihood of y given an x, and once you receive some y, you try to see that which of the x has the highest probability that this y would have been received. Okay, so you're just trying to guess that if x was 1, there is a 20% probability that y is 1 and 80% probability that y is minus 1. So it is if I receive minus that value, it means there is a higher chance that the received signal was x, because if that was the case, then this y is more likely. So this is called the maximum likelihood decoding or estimation, because you are trying to find for which x this particular value of y is maximum likely. Now suppose each bit is not equally probable. So in that case, some values of x can occur with higher probability. So in that case, there should be some bias, right? For example, if we know that 0 is transmitted 99% of the time and 1 is transmitted only 1% of the time, right? Which means that if we received some symbol, there is a higher chance that 0 was transmitted, regardless of what value can be. So we need to put some kind of bias there, and that bias can be understood in this the following way. Instead of talking about y given s, we talk about the probability of x given y. Okay, so we do not know x, so we only know y. So it is more intuitive to talk about given y, which x is more likely, right? Earlier case we said that given y, we are trying to find that x that which if would have occurred, this y becomes more likely, right? Now the more intuitive and simpler way to talk about given y, which x is more likely, right? And from Bayes' rule, you can say that probability the x given y is proportional to py given x into px. This px is the distribution of x, which we also call prior. So it makes sense to choose x which has the highest probability to occur given the particular value of y. And in other words, we select x that maximizes px given y, which is nothing but the maximum a posteriori probability. That is why we also call it the map estimation or map decoding. So we have talked about maximum and map decoding, and the total error in decoding would be probability that x is equal to -1 into probability that there is an error plus probability that x equal to y into then there is an error given x was 1. Right, so you have this conditional error that given x is -1, what is the error? Given x equal to 1 error, and you multiply with the probabilities of 1 and -1 and you get a total error for decoding. So you can also try to choose a decoding which minimizes this error. Similarly, the mean square error is given by the expected value of x hat minus x square. You can also choose a decoder which minimizes this error. We call that MMSC minimum mean square estimation, because we are trying to minimize the mean square error. Now let us go back to this example where we have treated the channel as between B and B hat, and there we have this relation between B hat and B. Right. So if suppose the noise is symmetric and zero mean, in that case P0 and P1 are simple, and what we get is a something called binary symmetric channel. So this is binary symmetric channel given 1 or 0. So suppose the bit is 1, there is a 1 minus p probability you will receive 1 and p probability that you receive 0 or b hat is 0. So this is b and this is b hat. So this p is the error probability. Similarly, if the bit 0 was transmitted, there is a p probability that it flips to 1. Now suppose bit 0 has q probability and bit 1 has 1 minus q probability. So in that case, total probability of error is qp plus 1 minus q into 1 minus p. Now if you send a bit stream 1 by 1 bit, there will be errors. Right? And the error, there is a p probability. So each bit, if I am assuming the independent channel, then each bit has a p probability to be flipped. So if I send 100 bits, I would expect 100 p bits to be bad. Right? But there, we know that we cannot send one bit in each slot. Or even if we send, there will be some loss. So some of the bits will go or some of them will not go. So on the average, we will not be able to send the same number of bits. So question is how much of how many bits we can send, what is the bit speed we can achieve here. And one information, is it possible to reduce this error? So you can see that if we suppose send 2 bits, same bit again 2 times, right, and the probability that both will be wrong is less. So it gives us some hope that maybe there are ways you can get a successful communication via this channel. So in the starting I said the communication is about sending some information from one end to another end. And what is crucial to understand here, which is not still discussed, is what is this information? So in general, I gave some examples of information that can be audio or a picture or anything. But the way it is, you can define it is, it is something which receiver does not know but wants to know. Right? It can be a decision or fact, anything which receiver does not know, but it helps in some process to the receiver, that we call information. Right? And these are the examples. And I said that these information examples can be represented by a sequence of numbers or bits. Right? Bits are just binary numbers, so you can equivalently represent anything by decimal numbers or hexadecimal numbers also, if you can represent them by bits. So a decision can be 0 and 1. There are, suppose, a decision which has 10 options can be represented by a binary number, a decimal number. The audio message can be sampled, its amplitude can be either represented by a sequence of numbers, decimal numbers or bits. But the question is, we know that these the bits can represent these information examples. But can bits represent every kind of information? Right? Is there anything more to it? So it turns out that not only bits can represent every type of information, it's actually the bits itself are a way to talk about information, a way to measure how much information is there. So before that, so we want to ask 2 questions here. How do we measure information, and how much information can be sent in a communication system? So first let us talk about information in an event and here we see how the bits and information are actually related. Suppose a quantity x has 2 possible states, right? And receiver want to know this quantity x. So the knowledge of the current state of x is an information, and it can be represented via a binary bit. Right? It has 2 values, 0 and 1. So you can assign each numbers to these 2 states, and then you can transmit that bit corresponding to the current state of X. Similarly, if quantity Y has 4 possible states, then you need 2 bits, right, to represent, so each combination of 2 bits will represent 1 states and 2 bits can represent 4 states. So we say that the knowledge of the current state of Y has 2 bits of information, right? The state is telling me one value out of 4 values, right? So the information is worth 2 bits. So each random variable contains a certain amount of uncertainty, right? If it has many possible values, knowing what exact value it has, right, has higher information. It means if the number of possible outcomes of X increases, you can expect to get more information from each outcome. And you can think in this way. Suppose X and Y are 2 random variables and each takes 2 states. So if I know the value of X, I have one information bit. If I know the value of Y, I have another information. So together, if I know the states of both these random variables, I have 2 bits of information. Now, if I combine x1 together to make a random variable z, a random vector, then z can have 4 possible values, 0, 0, 0, 1, 1, 0, 1, 1. And if I know z, I am also knowing the value of x or y, or similarly, if I know x and y, I know the value of z. So z has 2 bit of information because it tells me about x also, which is 1 bit, and y also, which is 1 bit. So each random variable has a certain amount of uncertainty because we do not know what value it will take, and once we know its value, we gain that information, right? So that information is what we say that the information in a particular outcome or in a particular event. Now each outcome may not have same amount of information, right? Suppose a random variable x takes 1 with 99.9% probability and 0 with 1%, 0.1% probability. So if you observe 1, probably you are not getting much surprise, you're not getting much information because you have already expected the x to be almost 1. But if in an outcome you receive 0, which means you have received some information. So whenever you observe an unlikely event, right, that observe has high information. You can think from a lottery point of view. Suppose you you bought a lottery and there were like total 10,000 different numbers, right? Now if I tell that this number has not is not the winning combination, that does not give you much information, right? Because there are 99 the 9,999 such numbers, right? But if I tell you what number has 1, that has more information because that number has a very small probability to occur. So if I tell you about which is the winning number, that has more information that telling you that another number has not 1. Okay, although each of these numbers have almost same kind of probability. So we talked about that if a random variable takes 2 values with different probabilities, they both outcomes does not have the same amount of information. This is true with any event. So if there is a event E with some probability, the information it contains is does depends on the probability of this event. If it's a rare event, then knowing that that event has occurred gives us more information than a event which is almost certain. For example, if you know that x will always be 1, if I know its value, does it give any information to us? So based on this intuitive understanding of the information, what the mathematical way to define this information, or the amount of information in event E, is given by minus log of probability of E. So if probability of E is 0, I mean, if it is 1, the information is 0, and if it is, if the probability decreases, it has very large information. And as E goes to 0, the information in that event increases. And if a random variable takes multiple values x, then the average information in the outcome of random variable is the expected value of information in each value, or occurrence of each value. So if x takes value x, some range of x, then if I weight by probability of x to compute the expectation, for me the average information in the random variable x is given by minus summation of px into log 2 px and minus sign. This is also like average uncertainty in the random variable x, and once we know the outcome, this is the average information we get. And this also denotes the required number of bits that can represent the outcome of x. So that is why we say that the bits is not just one way to represent x, but this is the fundamental way to represent information, because you can measure the amount of information by number of bits. So if k bits are required to represent random variable x, the information in that random variable is actually equal to k bits. So the question arises here, why does probability distribution of x changes the required number of bits? If x takes 8 values, then probably we need 3 bits. So how does having a different, how does the probability, specific probability distribution of x does change the required number of bits? So suppose y has 4 possible states with probability half, 1 by 4, 1 by 8, 1 by 8. Then we can, if we assign 2 bits to each state, then we of course need 2 bits on the average. But we can do better. We can assign a variable length bits to each of the state. So the most probable state A, we assign 0, which is 1 length. B we assign to 1 0, C we assign to 1 1 0, and D we assign as 1 0. Sorry, 1 1 1. So this way we make sure that even if we repeat these bits, there is no ambiguity. If I say 0 0, I know there AA is repeated. Right? If I say 0 1 0, which means A and B are in the sequence. So there is no ambiguity here. And still we are able to represent all bits. And the number of bits required here is 1 into, this is the average number of bits, so you have to multiply by probability. 1 into half plus 2 into 1 by 4 plus 3 into 1 by 8 plus 3 into 1 by 8, which is 1.75. So average information in y, or average number of bits is required in y, is 1.75, which is less than 2. So of course it has a little bit less information than if this all bits were equal probable, then we would need 2 bits. So the number of bits, this is one way 1.75 is required, but the best approach is given by the amount of information in y. So let us compute the information in y, which also comes out to be 1.75. So we say that this method particularly approaches 1.75, which is also the number of bits required by any approach. So this is number of information, the amount of information is equal to the number of bits required. Right. It may happen that sometime if you use just this particular example, you may get a little bit higher number of bits than the information contained in this. This means just that this is not the best approach. Maybe there exists some other approach which can give you a better type of assignment. So if these states were actually equally probable, then you can compute that the average information in this state is 2, so you require 2 bits. So here unequal distribution leads to some highly informative outcomes and some low informative outcomes. Right? If it was equal distribution, uniform distribution, then all of them has the same information. But here unequal distribution leads to some highly and some low informative outcomes, and because of that the average information is reduces. So average information is high when the all outcomes are equally likely, right? And this is because when all outcomes are equally likely, there is a almost in all the outcomes there is the same amount of surprise, and you can't really tell what outcome will be. Right? If there are two outcomes 0 and 1, if one is 99% and 0 is 1%, then you kind of know that 1 will occur. Right? But if both are 50-50%, basically you would have no idea what the next outcome would be. So that's why we say the surprise is high, so the information in that is also high. Now we also talk about mutual information. So a random variable contains some information we are interested in. But suppose we are not able to observe that random variable. What we observe is another random variable y, which we hope that it is dependent on x, right? If it is not dependent, then of course it's hard to guess anything about x. So now question is, if y and x are somehow dependent, what how much information can y tell about x? So we denote this by ix comma y, and there are two things we can observe directly even without going to the details of it. If y is equal to x, which means we know everything about x, so knowing y, we know about x. So the mutual information, which is the information in y about x, is the complete information about x. So that should be equal to hx, which is the information in x. And when y and x are independent, then basically y does not have any information about x. So in that case, the information should be 0, and that should be the minimum. And for other distributions or dependencies, the information should be in between these two, right? And it is also equal to the decrease in uncertainty of x when y is known. So x has some uncertainty, or and when y is known, that uncertainty decreases, and that decrease is a mutual information, the information about x what we get. So the equation of mutual information is given by this. You take the joint distribution. So this is basically the expected value of this particular term with a minus. So we divide the joint distribution by the marginal distribution product. We take log and compute this. So if these two are independent, then you can prove that this is equal to 1, so mutual information remains 0. So now the question is how much information you can pass via a channel. Let's talk about this particular case. So here you transmit X and you observe Y. The information you are able to pass via communication channel should be Ix, Y. Because you are only observing Y, so the information about X, what you get is just the information what Y has about X, which is nothing but the mutual information of X, Y. So it is possible, although, to choose a distribution of X which maximizes Ixy. See, so remember we have to transmit some bits, but we can of course choose the symbols we are going to use. So in that case, you can possibly choose some kind of distribution such that, or some kind of encoding event such that the distribution of X is such that the mutual information between X and Y is maximum. So the maximum information which you can pass via communication channel right? By optimizing the distribution of X or Y is known as the channel capacity. So you cannot change the channel. The channel has a particular capacity, and if you access some particular distribution, the distribution is kind of fixed, so the mutual information is kind of fixed. So for a particular distribution, this is the amount of information you can pass as IXY, and if you optimize it, this is the maximum information you can pass via this channel, and this is the best you can do, which we also known as the channel capacity, and is a property of the capacity. If you so there is a way to find a method, a transmission method, such that you are able to transmit these many bits in each slot probably, such that there is no error. So this channel capacity is also measured in bits, right? It is basically bits in kind of each resource, and on each slot you can talk about. So if you talk about this particular channel, the capacity here is computed by this particular formula, and you can see this in terms of P. So if P is half, which means 1 can flip equally with 1 and 0, this means basically Y and X are independent, and you cannot observe anything, cannot say anything about X by just knowing Y. So the information is 0 in that case. But as the P goes to 1, right, which means, sorry, P goes to 0, which means Y is equal to X, you achieve the 1 bit, which is the capacity of this channel, because you are sending 1 bit here. So you should be able to receive the complete bit. Right? That's how much information you can pass. And for other values of P, there is a particular value of P which you can compute from this. Now, how to achieve it, that's a different question. This does not tell what kind of algorithm, what kind of coding we can use to achieve this channel capacity, but this is the best what we can do. And one example which I will give here in this case is, which does not exactly achieve the capacity, but it is one way. It will at least achieve, so suppose we want to repeat the bits 3 times, and then we chose the majority of bit states. In that case, the probability that 3 bits, right, the majority will also be wrong, is the probability is very small, right? So by increasing the repetition, you can improve, you can reduce the error probability, and maybe you can say that under some probability constraint, you should be able to transmit, right? You should be able to transmit with very high, very high reliability. Right? But this is of course not the best, so there would be better encoding methods. Right? We are not going to talk much about that, but there is a whole subject about coding theory and the channel coding, source coding and channel coding, which talks about how do we achieve that. What I am going to talk about here is the channel capacity of AWGN channel, because as I said, this is very popular, simple, and yet very powerful channel. So AWGN channel is Y equal to X plus N, where N is some Gaussian noise. Channel capacity here is given by log 1 plus P by sigma square, and there is a half factor in some approaches. But let's ignore that factor for now. So P is the power of X, and N is the power of this expected value of noise, sorry, variance of noise. So this is when you do not have a constraint, but if you have some fixed bandwidth, then that basically limits on how fast you can send symbols. So in that case, you can transmit as B into log 2 1 plus P by sigma square. So as P by sigma square is also known as noise, signal by noise ratio. If that is very high, you can achieve very high capacity. But if this is low, this actually the capacity decreases. So this particular theorem is known as Shannon-Hartley theorem, and this gives the maximum data rates bits per second, right, which is also say BPS. So this gives us the maximum data rate and this formula is very popularly used in computing the performance of communication links, where our goal is to talk about the data rates, right? And if a channel has high data rate, which means you can pass more information or information faster, which means you should be able to communicate or send high data rate up. High data rate information. Sorry, this means that you should be able to send a huge amount of data in very short time, right? And which is very essential for today's world.